You ready for me?
Go ahead.
Okay, so I mentioned that the building up of LIGO wasn't done by any of the strategic planning. There was no yellow bar that was defined by somebody else or R&D funds at the labs. It was done in a much more entrepreneurial way by Kip and others. And that brought it to the point where the details in between kind of turning it into a construction project from R&D and who you convince and all that, I'll leave that for Kip. Then at some point it gets to be a construction project, and what I want to do is not give you a cookbook for how you organize a construction project, but more interesting is kind of just the general features and the puzzle then of how you get from that to a research environment thing, because some things are quite orthogonal. In terms of kind of the organizational structure that you talk about when you make an organization, people talk about flat organizations and vertical organizations. What does that mean? A vertical organization is one that has basically reporting above at every level, and it slowly comes to the boss at the top. So that's a total vertical organization, and it has every task broken down at some level. You know, it moves down at some level, and every task has a budget manager, who you report to, has deliverables, something you build or make or calculate and hand off, and you're judged by whether you did it within your budget, time, and so forth, and that it all comes together. That's the most traditional way you build any typical construction project. You know, if you build a bridge, that's what you do. That's you build a building, you build an airplane. That's the scheme that's used. The amount of extra things in an airplane compared to a bridge have to do with integration and quality control. Those are the added features that are kind of outside that you have to do, certainly for a science project. But the basic kind of guts of the organization is something that's vertical, and everybody and everything has a budget, a box, a person in charge, you know, people that work for them, and then they report and deadlines and so forth and so on. And that's what works. That's what's been built. That's what's built almost everything you look at outside the door and so forth. So you want to be as close as that as you can. I mean, we're clever as scientists, but it takes guts to feel you're going to do something different from kind of what works and make all the things happen, the right budget, the fact that you have to deliver things, the reportability, and so forth and so on. So you want it to look this way. But the research environment that I talked about, if you actually talked about it in organizational terms, is what you call a flat organization. It isn't vertical at all. You decide in the morning which lab you go into. Nobody's reporting to somebody every day. There's not the hierarchy and so forth and so on. So you want it to be, it's never completely flat, but a real research organization is kind of as flat as you can do. So everybody's a colleague, and you go next door and you decide what you do and so forth. So that's the pure thing. So it's not so simple to think how you build something like this and end up with something like this. And it's the trickiest part. For us in LIGO, we have a very flat organization at this point. We have separate groups operating, each of them like these small laboratories I talked about at the beginning. They have a few people, no more than in a small lab, and they do different projects. On campus, we have the 40-meter. It's being run by Alan Weinstein, and there's a postdoc and a few students and technician. We have what's called the thermal noise interferometer, Eric Black, and I don't know how many people do you have, Eric, over there? 3 or 4? 3 total, including a grad student. We have other advanced R&D projects that are all that size. Data analysis is a little trickier. I'll come to that because there's a certain amount of it that requires larger infrastructure to be able to do it. And it has to do with not the data analysis itself necessarily requires it, but the amount of data that you have and the amount of computing facilities that you have require a certain amount of organization. So data analysis is an area that's a little bit hybrid. You'd like to keep it as much like these as possible, And it's tricky to figure out how to do that exactly and have all the common infrastructure and reliability that you need. And then if in a flat organization, I'm going back and forth between these two, but in a flat organization, like we are in now, it's a research project, you want to be able to do new projects. So when we talk about advanced LIGO, now you're in the wrong organization. You're building advanced LIGO and you've created a flat organization, so you have to take a piece of it and make it look like that. So that's a little tricky. And lastly, as you turn this thing into a research organization, I talked about open data for NASA. Our scheme for including the broader community is to create a very large and open collaboration so that people join LIGO itself, what we call the LIGO Scientific Collaboration, and they have their data access through that, but then they abide by the same guidelines and rules that that group does. They have peer review inside. I mentioned that these collaborations have their own peer review and so forth, which gives reliability and a little better chance that people won't do stupid things and say stupid things and so forth. And so we've chosen to have the open data access through people joining this collaboration. The collaboration for LIGO to build the construction project was Caltech and MIT. It involves about less than 50 scientists, maybe 40, something like that, scientists. And that's what was needed to build the basic instrument and do some of the R&D that we're talking about. The LIGO scientific community, as it's grown to do this, I don't know what the latest numbers are, but it's over 300 scientists from about 5 countries or 6 countries, and maybe about 25 identifiable separate groups or institutions. So that's this open part. The other thing about what we're doing compared to, say, the NASA model, when we built this vertically, is that every piece of these, I talked about all these boxes in some vertical organization like building a bridge, but key to us being able to make sure we had the quality and the demands that we have inside LIGO was to make sure that each of these boxes had a responsible scientist, so that the project at all levels was guided by scientists, not by just engineers. It's not just that scientists are smarter, but there's an investment in the product. We're the ones that have to use it. We're the ones that have to not just know the best, but we're the ones that have the investment and have to live with it afterwards. As good an engineer as you might hire to do this, he goes on to another engineering job when he finishes it.
As I recall, the scientists weren't necessarily the bosses.
No. In some cases, the scientists are the bosses, and in some cases, the scientists were basically side by side with the task manager, who was more able to do that thing. So we had something we called a liaison scientist, something like that. I forget the name we used. Okay, just to give you a feeling of what these things look like, I'm not going to go through this, but this is an old one. I just grabbed it. I covered up the date. It's even got our old logo. But these are the kind of schedules that you make when you build this. This was approved in 1994, and we made a schedule that went out through 2001, but it's got all the pieces, all the equipment that you build, vacuum equipment, beam tubes, and so forth, the period of design, the period of construction, the period of installation, the whole thing designed to where it comes together so that you bring it together in ways that the experts can work on different things at different times. And these are the 2 different sites for the 2 different LIGO pieces. So those are typical high-level, what we call a summary schedule. We call it an integrated schedule because it has the whole project together. And then this is where the accountability, this is a typical accountability graph. The trick here is to ensure success. It's a little bit like these performance metrics. When you're contracted to do this, is to make a list that satisfies somebody that they're all the things you really want to do, and also ones that you feel confident that you're not going to get embarrassed by. So we made a whole list of this is for the facilities, and there's another piece of it for detectors. So we had 2 lists. just a finite number, over a period of 6 years, about a dozen what we call milestones, things that had to be completed at a certain time. You know, when do you occupy the buildings? And you can look at what's in what we call the PMP. That was the project management plan. It's a thing that had to be approved before they would give us any money. So we had to write this down before they give us any money. And you can compare all those dates with when we actually finished these. These were all finished, and they're all within a month or so the same for 6 years. So we managed to succeed because we defined our success properly. And the same thing for the detector. So there's a whole bunch of milestones that bring you up to coincidences. Money. You can also plot how you spent the money. This project costs almost $300 million. And how do you determine how much it costs? Let me just say a few words about how that's done. And I'll talk about another word that you hear, and then you'll see the philosophy that we used for something called contingency. So it's important, of course, to spend, to estimate properly the cost of a project. How do you do that? You could do it, you know, if you do something kind of at home and you build something, you just kind of guess at it and you add something and build it. And here the stakes are a little bit higher, so you have to try to do a little bit different discipline. So what we did is take, and this is not just us, but the scheme sometimes is different, but the scheme I'll give you is the one that we use. So we create this vertical thing with all these boxes, and then we go down to absolutely the lowest level possible, and whatever widgets there are or pieces you need to put together as defined as they are, and some of them are better defined than others. And we take each one and we ask what it costs, and not allowing ourselves to do anything other than give the best estimate we possibly can. No fudge factors. So you get the best estimate you possibly can on the numbers at the very bottom. And those numbers then are added up, and in our case came to something like, I'll show you the final thing, but I think it was something like 240 or 250 million out of 290, out of a budget of 292. So 240 some million dollars was just going absolutely to identifying everything, and you're really, where you mess up there is the things you forget, or things that you really somehow misidentify or misdesign, things that you just have to redo completely. But otherwise, that should be pretty good. If you've designed it and you know all the pieces, you should be able to get those pretty much right.
This includes salaries, I presume?
Yeah, includes salaries, and you do it in today's dollars. So you do it all in today's dollars, then you estimate something about inflation in the budgeting. So then you end up with $250 million. Then what do you do to take care of the rest? What is contingency? The idea of contingency is that things don't cost what you estimate if you're as honest as you can be, but instead they're going to cost somewhat more, but the amount more depends on what it is. So what we do is go to this very lowest level and take every item then, whether it's something you can go out and buy or something that's in Kip's head, and we basically assign a contingency. And the contingency that we used, I don't remember exactly, was something like 4% on anything you can find in a catalog. Because maybe by the time you buy it, it's that or it's gone up a little bit. So anything you buy in a catalog is 4%. Anything that we have some preliminary bids. Preliminary bids, you have to realize, are never the same as what somebody will actually sell you something for. That's when you go to some company and ask them what will they do this for, and they come back. And so we assigned, I don't know, 10 or 12% to that. So any item that was that we had some sort of piece of paper that said some company had looked at it or somebody had looked at it, we assigned 10 or 12%. And then anything that an engineer actually did a design, detailed design, was, I forget, 22%. And anything that was not engineered, meaning it was in Kip's head, or a notional design, if you want, of a physicist, in order not to embarrass us entirely, we assigned 98%, not 100%. So it's 98%. Those numbers come about from some history. I knew that use those numbers because it was the way I had done things in high energy physics, where there's been enough previous projects so that we know how well these contingency numbers, I oversimplified it a little bit in telling you, but we know how well they've worked over a series of projects. So you have the best reliable estimate of what all the widgets cost. You have the best possible estimate by knowing how those items are well known and kind of how much contingency. You add all that up, and so we ended up with something like 20% contingency that you needed, which meant most of ours was typically at the level of an engineering design, not a catalog thing that you bought, and also not just totally notional. Then,
I see the vertical going down.
What do you see? Oh yeah, okay, I'll explain that.
Why would it go down?
I'll show you. I'll tell you. So this graph here is the integrated spending, which should never go down, right? So we see it go down here. The integrated spending, this graph here is when we got the funding. So this is the funding. The funding should always be to the left of what you spend or you've spent in advance. In our case, we are very fortunate that the funding always preceded the need. Sometimes it doesn't, then you have to slow things down and wait for funding or borrow or something. This graph here is our design to spend it. And at some points we made some corrections. We decided to reduce some scope somewhere because we wanted to make sure that we didn't exceed this up here. So there's some knobs you can turn along the way. So these are kind of these little management decisions that I have to make along the way. And you can see I didn't bother with them very early. But when it got closer, we decided to, not put some rug on a floor and somewhere, some sort of things that there you could make choices and to make sure that it would be all right, and then add them at the very end. And I'll show you how you do that. So that's a knob you have, and then how you spend this contingency is the other knob. And I'm not going to show this because I want to get on to our status in a minute. Let me just show contingency. So this is then monitoring what happens to the contingency as a function of time. The first thing that happens is we made it grow a little bit. So we got a contingency by what the methodology that I said, and then we added to it. How do we do that? We took some things out of the project, like I said, right at the beginning, fancy rugs or size of a building or something. We decided we wanted a little more safety, things that we could add later. And we build it up by, it doesn't look like much on this plot, but it's $3 million. So we added $3 million in contingency at the beginning. And at various points along the way, we did a similar thing. We built up the contingency by deciding not to do something. There were some choices. And then basically watch this thing, and so that you basically want to get so that this is the amount of money that you have left that isn't committed, and you want to get to where you exactly spend the last dollar on the last day, and you don't have to give a penny back to the government, and you don't overspend anything. And that's just a tuning job right at the end just to bring this down. And we're still doing this very last piece. And the very last piece is easy for us because what we deferred to the very end is $3 million worth of computers. And of course, the later you buy those, the better computing you get. And if you buy 2.9 million instead of 3, it doesn't much matter. So it's easy for us to bring this right down to the last dollar, and we won't have to give a penny back. And we're heroes because we did it all right.
Right. It's a strange incentive structure, though, right? Because the incentive is to spend every penny, whereas if this were a matter project.
Yes.
The business organization, you might be rewarded. You might get a bonus at the end if you came in.
Right. In fact, some of the incentives are really bad here because if this job was done by, look, the incentive for me in doing it is to get the most performance out I can when this goes to zero. The incentive, if there's some projects now done on accelerators that I'm familiar with, and I won't name them, where this little bump here went way up. And what they do is an engineer takes control of the project, and then he's fine as long as this thing doesn't overspend. And so he wants to take a lot of money and build himself a big reserve. But he affects the physics performance, or so you almost need a scientist that cares in the end, because what you're really trying to do is, to answer your question, is get as much of the product that you want scientifically. So I got rid of rugs, but not performance, kind of. That was the idea. But you're right, it's a funny thing. But anyway, that's how it's done. This is just to show you how many people are involved. There's about 150 people. These are all the different, how many engineers, how many are Caltech students and all that stuff. But there's about 150 people involved in something like LIGO at Caltech and MIT and the two sites. And this is a fraction of them working on the construction project, rolling over to that different organization. The yellow here is the operations. And so as we rolled over into that, this organization was the one that's flat, and this is the one that one was vertical. They overlapped each other, and so it was kind of how you made that all mesh. And at this point, we're this totally research-oriented, flat organization trying to turn this on. So let me spend 20 minutes giving you a really quick view of LIGO itself and its status. But first, are there any more questions on the organization? I took a little longer than I intended, because I went broader than LIGO, but that's big science. That's how big science is done. Okay, so we started construction on LIGO. We got the first funding in 1994, and I showed you some graphs there where we basically did the construction and finished almost all the civil construction and spent almost all the construction money by 2000. Some of it's held back purposely, like the money for computers, because why spend a penny before you need to use the computer for something? You get better computing. So we've held back that. And a few other things, like some lab space and lab buildings that we want to tune to the last dollar. If we can have them, then we want a clean lab or this or that. So basically, but the instrument itself has been, the money in the device itself has been spent, and we've got what we've got. This is the Hanford facility. It's in eastern Washington, high desert, flat, mountains in the background, very stable. It's on kind of sandy surface, but very, very, very stable. And this is the 4-kilometer arms going out to here. And this is the central building, which is about 50,000 square feet and contains the business end of the lasers, the central optics that split the beams and so forth. They're all in this building. And then our office and lab buildings out here. And then we've built a second lab building somewhere near there. They're separated by, the two LIGO sites are separated by 3,000 kilometers. That means that a signal from anything in the universe can differ by a total of plus or minus 10 milliseconds, depending on whether it's coming that way, or straight down. So basically, in comparing the two, we asked for the signals to be coincident to something of the order of plus or minus 10 milliseconds. And the idea of that is kind of illustrated here. If we have actually two sites, but we have 3 interferometers. It's straightforward to put one extra interferometer that's not 100% independent. It's inside the same vacuum system, and it was chosen to be half the length of the 4 kilometers. So in Hanford, we have one 2-kilometer and one 4-kilometer interferometer. The 2-kilometer interferometer then, for a gravitational wave signal, should give half the size signal of the 4-kilometer interferometer. But for a lot of common noise that's just in the sites, they'll give the same size signals. That was the idea behind the two. The reason is that locally, you can lower the rate of just funny things that happen by asking for the coincidence. And then the coincidence between the two sites is easier to do. So there's 3 interferometers, but that's the strategy. Going to the previous history of having done a test on the 40 meter here, we had pretty good indication of what the noise, you've heard a lot about noise over the last few weeks, but what how Gaussian the noise is. And once the noise is non-Gaussian, you get a very long tail. Raising the threshold quickly loses sensitivity. So if you went to a reasonable level where you started to be in the non-Gaussian tail of the interferometer here on campus, the rate was about 50 per hour, that it just gave excess power above that level. Okay? That we felt was an upper limit on what a real interferometer would give, because the environment here is not very good compared to the quiet environment, say at Hanford or in Livingston. And so that's an upper limit. But we more or less knew how much common noise there was and how that would reduce things by doing a local coincidence and then a coincidence between the sites. The idea being that by the time you get the triple coincidence, you should have a false rate that's low compared to the event rate, or at least our patients, so that we had a goal of less than 1 per 10 years.
So these are the considerations.
Those are the considerations.
30-90s.
Yeah.
Decisions were made about
Right.
strategy.
Right. So that's the strategy. A second piece of just information, and I'm going to show you a little bit of data if we get a chance, is that the data recording, in contrast to a particle physics experiment, which is always triggered, you always have an interaction and a trigger somehow that you can form. You can keep, although particle physics experiments have a huge amount of data, they have the advantage that you can have a trigger, you can select how selective the trigger is. Here, we just take a time frequency series. And if you take the time frequency series, you get a huge amount of data. The amount of data in the gravitational wave signal is not the major contributor, but it's fairly big. It's about 0.2 megabytes per second. And the total amount of data is far greater than that, because we register a lot of things about the servos. We register a lot of things about auxiliary signals, environmental signals, so forth and so on. And we're not sure a priori till we start looking for signals which ones of those are important and which ones aren't. So we're reluctant to throw any of that away. So we end up with 16 megabytes per second of data, and that quickly adds up to a lot of data. So the short engineering run that we recently had in early January had something like 13 terabytes of data. And that was just a little test run. That's already enough so that it's hard to get your arms around it. It's a lot of data. We do data analysis both online and offline. By online, what we mean is either directly in the control room, where people get signals and they can maybe affect the instrument, or something that's done from the amount of data that we store locally on the disk quickly enough to give information back, maybe not directly online, but the next shift or next hour or next time somebody who is an expert sees something in the data to give back to the operators. We also then can use that for diagnostics, and we can do a certain amount of data compression. And the offline data is analyzed by putting it first in an archive, and we use the HPSS system in CACR here, and have built our own archive over there. Okay, so let's see where we are. We started, by the time we kind of got the money and then got ourselves organized, we started, this is a graph that I've used since 1994 with the agencies and reporting to them to just give them the absolute simplest highlight. What is the main thing we're doing each year? And with maybe a comment. So we started by, of course, clearing the sites and doing civil stuff. We've worked our way toward finishing building it in 2000, getting the interferometer themselves working, and now just beginning on sensitivity studies. So that's where we are now, and I'll show you that just quickly. And we expect to start our first really serious science run about summer of 2003 next year. Okay, I'm going to skip several of these or show you quickly, but there's a few features. This is a cross-section of the LIGO beam tube. It is an absolutely minimal thing. This is a beam tube. I've worked around accelerators my whole life. This is much more minimal. There's no services. So there's no electricity down it. It's just a shield to cover the beam pipe. The beam pipe itself is very large. It's 1.2 meter in diameter, thin stainless steel, 3 millimeter stainless steel. And it's big because it's our whole laboratory. So the whole laboratory is under vacuum. And it's at high vacuum, as you've probably seen in the noise curves. I'm not sure I have one. So this is what it looks like. It was made by a spiral mill that we made ourselves, or had made by industry. But You basically take a huge roll of stainless steel, 3mm stainless steel, rolled up like a roll of toilet paper, only as big as this here, and you unroll it in a way that just spirals out and makes the tube. So you're seeing the spiral here with stiffening rings to keep it stiff, otherwise it's like a piece of spaghetti. And that whole thing had 50 kilometers of weld. And by being very careful, because we were absolutely fearful we'd have leaks and couldn't find them, the classical way in the small physics lab is you helium bag something. You can't helium bag this. So we ended up with no leaks, which luckily, we thought we had ways to trace it, but they didn't. This is just an example. If we used a standard vacuum on this huge vacuum system, just pump it down, you get to something like 10 to the minus 6 torr. And the sensitivity curves that you've looked at are kind of here in a crude form. And that's pretty close. And in our scheme, where we're going to move down further as we improve LIGO, we want to keep all the secondary noise sources, the ones that aren't the primary ones up here, away from us. And so we couldn't just do this. So we had to create a high vacuum system out of this huge vacuum system. And you do that by baking out, by having it very clean and baking the whole thing out, which is a big process. That brings this background level lurking here down to this level here. And that's just an example of several things. This we did by borrowing magnet power supplies from Fermilab, running a current down the stainless steel, heating it up to 160 degrees C, and letting it bake for about, putting house insulation around it, letting it bake so it's very uniform, and then letting it bake for about a week, and that's the equivalent of a century or so of just outgassing otherwise. So you accelerate the outgassing, and then they...
Boiling off all the...
Yeah. And then at the end of it, you get to where you've improved things by 3 orders of magnitude. And,
How much was the power bill for the bake house?
Oh, the power bill was high. It was more than... It's hard to just... There's no power meter on that itself, but it was more than $100,000 per site just to bake it out. These are the big vacuum chambers, and what to notice is they're about 15 feet high or so, and there's a lot of ports. That's because there's a lot of different axis and different side beams and alignment things and so forth that you want to have. They are under high vacuum also, but what's on the ends of each are this thing here. See the thing here and here? These are gate valves, larger than you can buy commercially. They're 4-foot gate valves, and they close off this long vacuum. So once we make the long vacuum, which works at 10 to the minus 9 torr, we never change that. That stays baked out. If we want to work on a mirror or something in here, you close these gate valves, keep the long arms under high vacuum, and go inside the chamber and work on it. It all has to be done clean, but that's the scheme. This is inside that big building in the corner. This is just a more detailed view, but of the fact that what makes these tricky, other than the fact that it's optical tables, very clean and so forth, is that this kind of seismic system that you heard about has to be inside this vacuum and has to perform under vacuum and not outgas and ruin the vacuum and so forth. Let me not go through those. You've heard those things separately, so let me go on a little bit. I'm just going to do a few highlights. From the 40-meter studies, we have been able to test our ability to model these noise sources. This is a detailed model of the noise sources that has been done within LIGO, projecting from the real data observed in the 40-meter and calculations of some of them that are lower, and projecting what the sensitivity will be in LIGO itself. So the projected sensitivity comes from a model that has a reasonable amount of testing in the prototype, and so that's how you develop a model to do things. The optics in LIGO is actually very impressive. It's the same quality, more or less, that people use in optical telescopes. Lambda over 5,000 is achieved in these mirrors. They're quite big. The reason they're big is that the laser beam, of course, bounces back and forth some, but we want to contain the large tails on any of the optics. They're 25 centimeters across, 10 centimeters thick. And then we map each of them. The idea eventually being that the mapping of the surface is included in the simulation program, so that the detailed simulation program actually knows the details of the mirrors that it goes through. These mirrors, since you go into it and you have to pass through the mirrors, also have to be optically transparent, not heat up too much and so forth, so they have very low absorption, very low scattering, and so forth. You have to work clean around all these things, and they have to have the feature that they're, whatever inherent noise they have, thermal noise, whatever noise, we can keep it out of our frequency band, and so they have what's called high Q. These are the Qs as measured for some of these mirrors. The laser we have has to be have you talked about the lasers? Okay, the laser itself that we use is a single line laser, and it's a continuous laser. It was developed at Stanford by some of our collaborators and was developed far enough so we were able, and this is something that you'd like to point for in experimental work, is we could commercialize it. We managed to be able to talk a company or get a company to build it for us, which means not only that they service it, but they make it reliably. They've turned it into something in their catalog. And the last thing we want to worry about is the performance of our laser. We want to worry about LIGO noise sources, not the laser itself. We want it to be really, really reliable. We've used that laser for a long time now. I'll show you a little bit. No, maybe I won't. I want to show you locking, since you've seen locking in a film, to show you what it looks like in a control room. Let me skip this. Okay. In turning on the machine, I'm just going to show you two things. I'm going to show you what happens in practice turning it on in a control room. First thing is the laser. I just showed you the laser. When we turned on the laser, it looked like this is a noise. This is just the frequency noise in the laser versus frequency. This curve up here is what it looked like when we turned it on. It's actually run for something like 20,000 hours continuously and not broken. So the first requirement that we had it done in industry was a good idea. And then we take this, and this is typical of any sub-piece of a big complicated piece of equipment like this, is measure its performance against what you want it to be. This is what was used in those performance curves. And then work on the reasons why it's different than that and bring it down. This graph is a little old, but because it's better now. But this is the kind of improvements that you get just working on it. And I'm only using as an illustration that what you do is work on any of these sub-pieces and make it work. And you also work on the overall performance of the whole system of LIGO. And eventually this comes down. I think this now is at its design performance, except for a couple humps at lower frequency. Okay, I want to show you the locking because you had Matt Evans talk, and he probably showed you more matrices and so forth. And I'm going to show you what happens if you're in the control room in locking the interferometer. By locking, of course, what we mean is that we achieve a resonant state, that these are Fabry-Perot arms, and we get them to resonate, the light to resonate and build up in the arms, and build up even further when we put in a recycling mirror.
Can you remind us what's being locked to what?
Yeah. The first thing we do is start with a laser, and it gets locked in steps. You basically start with a laser. It's the thing you stabilize. Then everything refers back to that and has feedback back to that. And step by step, you stabilize it. It first goes through a mode cleaner, a thing that stabilizes it and picks the central frequency. And then you bring it into what we call a central Michelson that you get stabilized, and you add one arm at a time and reference it back to that.
When you say stabilized, what exactly is stable?
Okay. This is just an example, for example, going back of the stabilization of the laser itself. If you just take the laser itself that comes out of its box, it has a certain stability. Then we have a requirement that we have feedback loops to make it stable more. And so we build a lot of electronics that just looks at the laser itself and feeds it back without going into any details.
What you mean is the power of the laser?
This is the frequency. So this is so what I'm going to show you is the frequency of the laser itself after we go through our electronics is stable to 10 to the minus 1 hertz per root hertz. Okay? Then we add a next step, which is kind of preparing it to go into the interferometer, if you want, what we call input optics. That actually stabilizes it further. Then when we go in the interferometer and make the interferometer work, it stabilizes it yet further. Okay, so
Stabilization is by this boundary or locking.
yeah, that you heard. Yeah, and you can see it stabilize in steps. Okay, so by the time we make the whole interferometer work, we can go back and look very carefully at the laser, and that's what I was showing you before. So I had skipped a couple steps. When I show you this is afterwards. So what I want to show you is this locking itself, or what you see if you're actually in the control room. And I like this particular picture because it's before it was very stable, so you can kind of see the features. And it was the time when we first began to lock it, so it wasn't really very stable. Now it's kind of uninteresting to see. It's either locked or something's wrong. So we lock first we do these steps in here and make all this work, and then eventually try to bring up a arm into resonance, or the other arm into resonance. So, and then finally both arms. So what I'm going to show you is a little video that shows the scattered signal from this recycling mirror, from the splitter mirror, and from the two end mirrors. And let me just say a few words before you see it. The size of the images is the magnification of the camera, nothing to do with the size of the image, size of the beam itself. Second thing is the images are white on a dark background. So as the resonance luminosity of the beam builds up, you don't see a whiter image, you see the background get blacker. So that's the two things to keep in mind. So as it builds up, you'll see the background get blacker. So what I'm going to show you is one of our first, what at that time was a long lock, because it shows you then the other controls you have to use using those cameras. So this locked for a couple minutes. Well, first I do one arm. So this is these two images. And notice the waving around. I'll talk about that in a minute. And then this one arm is locked. So we are able quickly to do one arm locking. This waving around is really the fact that at that time we didn't have stabilization in yaw and pitch. And so these are actually the mirrors moving around. If they move enough, then the whole thing goes out of lock. Okay, now I'll go to trying to lock the whole thing. Yeah.
So what was the amplitude of the movement of the mirror?
The amplitude in order to lock has to be less than 10 to the minus 10 meters in order to have a chance to lock. The actual amplitude that we're measuring here is, to see this, I'm not sure exactly, but it's probably 1 or 2 orders of magnitude lower than that. Maybe 10 to the minus 11 or 10 to the minus 12 meters, yeah. But they're slow in time. See, it went out of lock here. Now I'm going to show both arms locking, and you'll see it's trying to. Remember, it's just waving back and forth, and it has to try to catch it in the way that Matt Evans talked about. And you'll see one arm lock, and when the second one locks, you notice how black the background got. And so this is it locked, and you can see the arms, you can see the mirrors shaking around a little bit, and it stays locked for, at that time, a couple of minutes, when without the stabilization of the yaw and pitch and so forth, we couldn't hold it longer than that. Eventually, we could hold it much longer than that, and then we're limited by other things. And this locking was all done in this sequence semi-automatically using the calculations and the scheme that Matt Evans developed and talked about here. One of the hard things is just looking at this scale here. This is one of his plots, is that you start with a power that's on this scale 10 to the minus 3 and end up with a power up here that's almost 10. So you have got quite a few orders of magnitude of power buildup. And in order to see it down here, in the beginning especially, we turn up all our amplifiers and everything so we can see the beam when it's not locking, because we're having trouble locking. And then all this has to build up and somehow stay reasonably linear. And all these mirrors have on them 4 actuators. And you can imagine when things become nonlinear, they don't each saturate exactly the same. One one of the little magnets saturates before another one. And so that then it kind of goes out of lock in some funny way. So that's the kind of thing that does this. But it's a very hard job to get this completely to lock because it's a very large dynamic range and it's also nonlinear. So it's a control system with both nonlinearities and a very large range. This is the sensitivity that we achieved during our test run in January, or December and January. These are the three different interferometers. The 4 kilometer had just been turned on at that time, and this is the Livingston 4 kilometer, which is better at low frequencies because we've concentrated on low frequencies because there's external reasons that we need to there. And this is the 2 kilometer at Hanford. I think I better quit soon. Let me just, because I'm running over. This is just how far we have to go. So you can see where we are compared to where we have to go. And we haven't yet really started to concentrate on sensitivity. We've worked up through that run on making these things stable. Now that we've achieved that, we can now keep it stable for hours, basically. We've already improved it another factor of 3 or 4 in the weeks that followed. So I think I'll quit. There were a few more things I was going to show, but I think I'll quit here. Okay?
So could you go back to the noise curve that you were just showing?
Oh, sure. This one or the other one?
Previous one. Okay, so that's where you were in January.
Yeah, right.
And the next one is basically an improvement of something like a 3 or 4.
Yeah, right. So it's this curve down to about here. So at the higher frequencies, we're a couple orders of magnitude away at this point. At the lower frequencies, it's more than 3 orders of magnitude away.
Eric, what's the limiting noise source of high frequencies?
We're not sure exactly, but we're not shot noise limited yet. So we're not sure what the...
Okay, so that slope that looks like shot noise limited is...
Yeah. Yeah, you know, everything has that shape at high frequencies because the sampling gets shorter. It's just the natural shape that anything that's flat will have. What's the source of this noise? Most of our noise now is in the details of the control system or electronics, or pickup from the environment, meaning acoustic noise, things like that get back into the system. So for example, we had, earlier we had quite a bit of noise that was in the laser system because the laser, that fancy electronics I talked about was exposed. And any sort of noise, a pump vibrating, would make acoustic noise that shakes the table a little bit and affects you. So it's all external. It's not really, we're not yet at the point where we're dealing with the kinds of noise that you've been talking about in here. We're just not there yet. It's electronic of various types and acoustic and all the things that are just experimental problems. Once we get down near here, then we're dealing with those, but we're not there yet.
When do you expect that LIGO will be ready to detect gravitational waves then? It's the earliest we could hear a big announcement. We found something.
I think the first really, well, the way we've looked at it is the run that we're going to have. We're going to have a run this summer, which is about the same as that thing I called an engineering run, which is we consider an upper limit run. That doesn't mean no one will search, but it means it's kind of not the goal. And then we'll have one more in late fall that we call an upper limit run. Those runs should be the most sensitive instrument that's actually ever looked, even though it isn't very sensitive. So we'll do that. Next summer, not this coming summer, but the following summer, then we expect to enter into something like a 6-month run at whatever sensitivity we're at that point, which probably won't be designed, but will be getting closer. And that's the first chance, I think, to look, although, you know, we're not at our limit yet.
So summer of 2003, you think?
Well, 6 months of 2003, summer of 2003, 6 months of data taking, and then however long it takes you to digest it. So that's the first actual try. This is our first astronomical observation, actually, just that we can actually detect the sun and the Earth. Better than CERN. They do it by looking at the mass of the effect of the mass of the Z, actually.
Wow.
Yeah, by the fact that it stretches a little bit. But in this case, this is the long-term stretching of the Earth by the passage of the moon and the sun. There's two curves on here. One is the data, and the other is the prediction. The prediction was done the summer before we managed to lock the interferometer by a Caltech undergraduate surf student. And he did a pretty good job. He mapped the sun and the Earth. You know, if there's a few places where you're off by 20% or so, but it's pretty close. So he managed to give us a model that will work. We only recently, and this, after running for about 6 months with the interferometer, this thing, which takes about every couple hours, it depends where the sun and the moon is, but something like a couple hours before it stretches the interferometer enough or squashes it enough so that it's outside of our range and we lose lock. And we're now actually putting in the feedback, feed forward compensation for this, and managing to lock longer.
How does it compare with the existing measurement?
Which measurement?
How does the LIGO measurement for sun and moon's motion compare with the other existing measurements?
Yeah, we used the thing that is on an absolute scale. We're within 20% of. He used a model that's known from what, and it's within. What the big uncertainty is the crust of the Earth itself, and how much it actually stretches and squashes. This has a slight cheat. We renormalized to 20%, the calculation that he had. So the actual geology of the Earth at Hanford, where this was done, is probably a little bit different, but the features are the same. I haven't seen a better graph than that. I haven't looked very hard, but I haven't seen a better graph of the Earth tides than the one we've got, actually. Best one I've seen. I don't know if it's the best one.
Maybe this is a functional.
Yeah. Okay. So, all right, somebody's going to talk about data analysis later? Yeah, good. Good. Because that's what I was going to show a little bit. But okay.